Hello, I am Michelle Davis of the Center for Manufacturing Research at Tennessee Tech University in Cookeville, Tennessee. Welcome to the Fall 2019 Golden Eagle Additively Innovative Lecture Series. This is the eighth semester we produce this popular and informative series. The series is hosted by TTU's Center for Manufacturing Research and the iMaker Space at TTU. Additive manufacturing is the focus of both entities, and as such, this short virtual lecture series has been planned to highlight the best practices, potential problems, technological advancements, innovations, and scientific contributions in additive manufacturing, with expert talks from various institutions, industries, R&D centers, and laboratories. Today, we are honored to hear from Dr. Haijun Gong, assistant professor in the Department of Manufacturing Engineering at Georgia Southern University. His talk is titled FDM-based Metal Additive Manufacturing. The speaker will provide his contact information for questions after the presentation is over. Thank you, and I turn the presentation over to Dr. Gong.
Okay. My topic is about FDM-based metal additive manufacturing. My name is Haijun, and I'm an assistant professor of manufacturing engineering department at Georgia Southern University. And we're a new program, actually. The program started in 2015, and we are 4 years old. We just had our first couple of graduates this summer. And here are some pictures of our manufacturing engineering teaching labs. We emphasize on hands-on skills and as well as the lecture teaching. And we have a CNC lab, robotics and automation lab, additive manufacturing lab, microscopy lab, and also additive manufacturing is our focus on the research and teaching. All the faculty of different research domains have their own research labs. Okay. Now, the manufacturing engineering, the motivation about additive manufacturing of this topic is to reduce the cost of a metal additive manufacturing process. As you may know, the current commercialized additive manufacturing process is very expensive. So the laser-based, electron beam-based metal additive manufacturing process are all very expensive. For example, the selective laser melting, lens process, electron beam melting, ultrasonic additive manufacturing, are all expensive. We have a selective laser melting machine, and the machine costs are more than $500 million to start. For budgeting, it including the machine POE installation, operator training, facility safety kind of cost. So, but this is not desired for small business and the university labs. But the current rapid growth of additive manufacturing expects a more economic process for metal parts. And the stainless steel 316L has been widely used and researched for the additive manufacturing process. So, for example, the selective laser melting. But there's very limited research on extrusion-based metal additive manufacturing process. And 2 years ago, I was in a conference, AMA conference, and BASF introduced ultrafused metal filament for additive manufacturing. This is a metal filament. This is a metal polymer composite filament with high load of metal components, about 80%, and the other remaining contents are polymer. And this metal filament can make the metal additive manufacturing cost effective. And the filament has 2 diameters available, 1.75 and 2.85 millimeters. So you can directly use this ultrafused filament for 3D printing. Use a very cheap FDM-based 3D printer. So what the 3D printer I use is just a flash for dreamer 3D printer, and it originally used for plastic filament, but now it can take ultrafiled filament for 3D printing for metal part. And the part printed is a green part. It's not pure metal because it has a polymer contents inside. So we need to make the green part to be in the furnace for the bending process to remove the polymer contents, and then use a sintering furnace to make it to be metal. So this kind of alternative way to make a metal part using FDM, and the thing is that it has some shrinkage, as you can see from the demonstration illustration for this process. The metal part is a little bit smaller than the green part. Any 3D printer, FDM-based 3D printer has a Bowden extruder or direct draft extruder can use this filament. And you can use a industrial standard debonding and sintering process to make the green part to be metal. Okay. Now, so for my research, the objective is to investigate the part property, including the density and porosity and the material microstructures, and to evaluate the mechanical properties such as tensile strength, hardness, fatigue performance, and the shrinkage. As you can see, there is a shrinkage for the metal part after the debonding and sintering process. So the shrinkage is critical for research. And I'll also introduce some cost analysis of using ultrafiled filament, and discuss a preliminary guideline how to select this selective melting FDM metal additive manufacturing for part fabrication. Now the experimental metal setup is Flash for Dreamer FDM 3D printer. It's a desktop 3D printer, and it costs less than the selective laser melting machine. And here is a video to show the manufacturing, to show the 3D printing process of using ultrafiled filament to make green part. As you can see, it's quite same to using plastic filament. Okay, and there are some Wonder suggested processing parameters. For example, the nozzle temperature need to be heated to about 235 centigrade. The bed temperature need to be higher than 90 degrees, and it requires a low scan speed, and the layer thickness could be 0.15 millimeter to 0.2 millimeter. And for the millimeter filament, it's better to use nozzle with diameter 0.4 millimeter. So this there's a demonstration part, green part, and the center part. As you can see, after the 3D printing process, the part has a apparent shrinkage. Oh, sorry. And the testing equipment I use is a gas pacnometer. It's from Micromatrix. This is used for estimate density and porosity. And the tensile test is conducted using an Instron tensile testing machine. And the fatigue test is conducted using MTS Acumen 3 fatigue tester. And the shrinkage is evaluated using a Keynes system to measure the features of artifact part. Now for the density and porosity, I print small cubes. The cube is about 10 by 10 by 10 millimeter. And after 3D printing, the part is sent out for debonding and sintering, and then it became the metal part. and then the metal part is put into the gas pacnometer to estimate the volume. And I use a digital balance to measure the mass of the part, and to use the equation to calculate the density. It seems like the density is less than the selective laser melting part, and the regular stainless steel 316 part. The density is about 7.88 gram per cubic centimeter. So this is about this indicates about 1.5% of porosity. I'm not surprised about the porosity because of the FDM process. It's hard to avoid porosity or defects for the FDM part. There are always gaps between the contour and the infill sections. Okay. After that, the part is a section for microstructure characterizations. The part is sectioned vertically and horizontally. So there's pictures to show the microstructures of cross section. As you can see, all the greens have the similar dimensions in all directions after the sintering process. We can consider this to be a annealed condition for the stainless steel 316 alloy. And for the second picture, the arrow indicates the building direction. So different from the selective laser melting process, which has the multiple shape. For the FDM-based stainless steel 316, you can see there's no layer for each for the along the vertical building process. Okay. Now this implies that the center process sample is not high strength because it's microstructure but it's ductile. Its green morphology is independent of the orientation of the building. We can predict its isotropic material. And for the hardness, I use Rockwell hardness tester B scale to measure the FDM stainless steel 316L, and in comparison with selective laser melting stainless steel 316 and the ANSI type stainless steel 316L, and the value is about 60. Is less than the selective laser sintering. Select SLM stainless steel 316L, because for the SLM part, it has a higher dislocation rate. So the hardness is much higher than the FDM stainless steel 316. Now for the tensile test, the flat bar is directly printed using the 3D printer, and then it is sent out for debanding and sintering. And I use a strong tensile tester for the tensile test. So the yield strength, UTS, elastic modelers are evaluated using this test. It seems like the yield strength is much lower than the selective laser sintering than the SLM stainless steel, but it has a comparable elongation. The string about 30%. The UTS is about 65 megapascal, and I assume this tensile strength is attributed to the microstructures, isotropic microstructure, as well as porosity inclusion in the part, because there's always porosity in the FDM part. The defects cannot be eliminated after this debanding and the sintering process. And these are some SEM pictures about the fracture surface. As you can see the layers. It's very it's obvious to see to distinguish the layers of each print, of each layer print, and also you can see there are some gaps between the contouring and the infill region. And the included porosity is mostly located near the subsurface after 3D printing, and this defects can lower the ductility and reduce the tensile strength of the part. And for fatigue testing, I printed some round bars and put the round bar in the furnace for depending on and the sintering. So then I use a CNC machine to machine the round bar. You can see it has a smooth surface roughness compared to the as-built surface. So the fatigue bar is tested using the MTS fatigue tester. The thing is that you can see after the CNC machining, some porosity underneath the subsurface of the round bar is removed, so it has less porosity inclusion in comparison with as-built surface. So here, the porosity is minimized after machining in the gauge section of the fatigue bar. So this can explain why it has a higher stress when it is filled in the fatigue testing. So you may notice for some failure stress, it is even higher than the yield strength of that tensile test. I assume this is attributed to the defect inclusion of the flat bar. But when we machine the fatigue bars, those cross sections have less porosity underneath the subsurface, so it has a lot higher stress for the failure. This indicates that the round bar after machining may have a higher tensile strength in comparison with a flat bar. Okay. For the shrinkage, I use artifact part design using SolidWorks, and some features of interest. FOI is measured using the Keynes machine. The Keynes scans the surface profile, and then for the FOI, I measured both horizontal dimensions and vertical dimensions for each interested feature. Okay. So as you can see, the green part is almost the same size of the artifact part of the CAD model, but the metal part is smaller because of the shrinkage. So I measure the FOI in both directions for the features of interest, and then measure the metal part and make a comparison of both measurements. Okay. This is some dimensional comparison of both metal part and the green part. As you can see, for the geometric features in XY plane, it exhibits a size reduction about 13 to 18%, but for shrinkage along Z-axis, it has a higher percentage, about 18 to 23%. The shrinkage the shrinkage in Z-axis is influenced by the gravity effect, so it can cause a higher shrinkage in that direction. Now here are some preliminary guideline for using FDM-based metal additive manufacturing. So in comparison with SLM, the powder bed furan-based additive manufacturing process for metal part, so FDM-based metal additive manufacturing it's cheaper, and the disadvantage is that it needs size compensation due to the shrinkage after the debonding and the sintering process. The SLM part is expensive, but it's a process. But for the FDM-based additive manufacturing, it's cost effective. And also, it takes some time for debonding and the sintering process, especially if you don't have such equipment. You need to send it out to the third-party company for this service. As a user, you don't need to, but as a user, you don't need to hide the debonding and sintering surface. You can just order the filament to print in your FDM 3D printer, and then send it out to the third party surface for the debonding and sintering process. Okay, now this can have multiple users can use the same debonding and sintering surface, so it saves the cost to maintain the equipment if you prefer to do so, but you just need to pay for the logistics of the part, the shaping. This is extremely cheaper for the small business, for the university labs, which have limited budgets and less accuracy requirements. Here are some benefits of using FDM-based metal additive manufacturing. So the first is the investment for machine is pretty low. So you only need to have FDM-based 3D printer, which was used for plastic, as long as the nozzle can be heated to higher than 200 centigrade, and the platform can be heated. You can use the filament for 3D printing, and then you can send it out to a company for debonding and sintering. And the FDM-based 3D printer is easy to operate and maintain. The maintenance is pretty cheaper compared to the selective laser melting process. So you don't need to you don't have any trouble with the safety issue. With the safety, because FDM is less dangerous than the selective laser melting machine, and you don't need to use powder. Powder is usually hazardous to human health. Okay. The metal filament is affordable, it's easy to handle, and the usage of metal filament is always it's easy to predict the usage of metal filament. So there are many even free software can predict the usage of metal filament. So you can have estimation how much to use and how long, how often you order the filament. Now, also the FDM-based 3D printer is immediately ready for accepting new part after the green part is completed. Okay, this is quite different from the selective laser melting machine, because for the SLM machine, you need to prepare the build plate. You need to level the build plate. You need to after the 3D printing process, you need to clean the machine. It takes a long time to maintain the machine and to clean the machine. So this is a benefit of using FDM-based 3D printer. Here are some FDM metal parts I printed and send it out for debonding and sintering. This part all have the as-built surface, but after CNC machining, it may have the same smooth roughness like the fatigue bar I showed from the prior slides. Okay. All right. Thank you for your interest. This is some preliminary research about FDM-based additive manufacturing process for metals.